Yeah. Yes. So
Thank you, Rika. You have the microphone?
if the microphone, yeah, everything should all set. So this is going to be the last technical presentation today. So bear with me for the last. Yeah. So I'm Luca Cominardi, Senior Technologist at AdLink, and today we are gonna look more into AI aspects. So we have been seeing a lot of work on AI today, focusing on models, etc. But with today's presentation, covering some aspect of a Zeno project, we're going to see how that the brain itself brought by AI is not enough. You also need a nervous system to connect everything together, bring the data together. So I will start the presentation with this comic from XKCD that say that to complete your registration, please tell us whether or not this image contains a stop sign, so object detection. No, yes, but please answer quickly. Our self-driving car is almost at intersection. So the idea here is that you take your AI, you can distribute it, but how far you can distribute it and how long can you keep your system running when distributing your AI, and how this control loop can really work successfully in a real system. This is something of some question that we have been asking in this European project called Demon, where it's a H2020 project, research project, where we are also collaborating with some colleagues from the IMEC lab from Antwerp. Try to identify, okay, you have got your AI model. It works perfectly. You can improve your accuracy, but at some point of time, your AI model needs to work on a real system, and you've got communication between different components of your system, especially when you are distributing your AI. So what are the limits, and how really the different components can communicate with each other while complying the overall objective of your AI? So it's not only the model that makes the optimal decision, but also your nervous systems that really interconnect all your pieces of your model. So it's a bit like the human body, right? So we've got sensor information coming out from, for example, the fingertips that needs to reach the brain. The brain takes an action and then sends back the signal to your arm to do something, for example. So this is how it works, our human body. Why should be any different for AI? So what is our nervous system for AI? So let's try to get a bit of context about data, and data when we really distribute data on this IoT, edge, and cloud. And by looking at any data journey, so the journey that your data does, regardless on the type of any modern application, right? So at some point of time, you've got data that is produced. It can be a sensor, it could be a camera, it could be whatever. You have got something that produces data. This data is pushed then in your system and is distributed. So it needs to reach the point where it's meaningful, this data. At this point, this data is either computed, so you do something on it, or you store it. And once you store it, it means that you are gonna wanna do something later on that data. And at this point, all the cycle goes on. So you compute it, you want to push back again your data for the next computation, or your computer, you want to store it. Or once you store it, you don't, you leave the data, but some point of time you want to pull the data out of your storage to do an additional computation. So if you look at these patterns, you can see that we've got two main patterns. One that we call it data in motion. So we've got data that is being distributed, it's live, okay? It's moving in your system, in your network. And data rest, that is data that hit a storage. And at some point of time, it's stuck there. So it doesn't move until you decide to take it back. In this approaches, we've got data in motion is mainly push-based, while data rest is pull-based. So you decide when to take it. And if you want to really bring an very important aspect while bringing this kind of system at scale, when you want to really distribute your system that are from the tiny sensor up to the edge, to the cloud, and having multiple applications that deal with data, location transparency becomes a very important aspect to deal with data. So if you need to keep track of every data, where it is, who produces, how to retrieve it, becomes very hard to deal with a system that goes out of scale. So location transparency is something that you really would like to have when operating at scale over a very distributed decentralized system. And as I said, decentralization is also one key point. So we have got this trend about edge computing nowadays. Let's push data. I've been hearing today also. Let's data gravity. So let's compute the data where it is produced. Okay. Let's try to keep data locally without the need of distributing your data where it is not needed. Just keep it there, right? But at the same time, you want to keep your data distributed. But through location transparency, you can have a single logical view of your data that is harmonized without the need of keeping track of all of it. So location transparency coupled with decentralization is something that is really needed when really going distributed. So what this brings us to? Brings us to the motivation. We just seen the motivation of the Eclipse Zeno project. So Zeno is an open source project under the umbrella of the Eclipse Edge Native Working Group that AdLink is very much involved in. And the idea of Zeno is to provide a project that unifies data in motion, data in use, data rest, and computation. So I've seen before that you've got different data patterns that as of today, you need to take different projects separately and need to do some patchwork design to make it work, really to have an end-to-end semantics of your data. With Zeno, you really want to bridge them and to have from end-to-end semantics for different data patterns that are used by any modern application. From the tiny sensor, like an Arduino, up to the edge server, up to the cloud data center. And it's also introduced not only the data motion of data rest, it really brings down this concept of geo-distribution of data. So keep the data wherever it is needed for also privacy, load balancing, for any type of reason you would like to keep your data distributed. So from a point of view, from a network stack point of view, right? So Zeno is a product that provides high-level API for high-performance pub/sub and distributed queries. Data representation transcoding, for example, passing from JSON or any other type of data representation, and implementation of geo-distributed storage and distributed computed values. So it really goes into the distribution of your data and dealing with systems that are decentralized, and you could have part of the system that could appear or disappear while running. So really dealing with distribution at the core of the concept. So for what concerns the high-level API, at the moment we support out-of-the-box Zeno Rust. We've got a Rust APIs because the core of Zeno is implementing Rust. We've got a C API, Python API, and also we've got a parallel stack that's called a Zeno Pico to really go for embedded device like Arduino Lite. So in the picture, you can see a network stack representation of where Zeno fits. You can say that Zeno sits on top of any different multiple different network stack layers. So you could have for example, Zeno on top of a TCP/IP, on top of UDP, on top of TLS, on top of QUIC, but also on top directly of Bluetooth, really LoRa or narrowband IoT. So it really goes down to the network technology you can put Zeno on top that will work. So we're not tied to any specific system implementation, system and deployment. And this brings us to what kind of communication models we support in Zeno for communication. We can see that the first type of communication model we see is peer-to-peer. So we've got, for example, a fleet of vehicles, fleet of robots that can communicate with each other. So you don't need an intermediary point, for example, like a broker to communicate through. You can really communicate directly with each other, both in a click topology or in a partial mesh topology. The second type of communication model that we support is the brokered mode. For example, for small clients, like small Arduino sensors that they connect to a broker, and the broker it will dispatch the data for you. And if you want to bring everything together, the overall picture, you also have the router communication model. So you can bridge them all together where we've got peer-to-peer communication. But if you need to communicate from other part of the system where you are not directly connected to, you can go through a routing infrastructure provided by Zeno. And the same things, you might have the client communicated to peer in any type of combination. So depending on your deployment, you can pick your the communication model that is most suitable for you. But how we can manage, can write an application on top of Zeno. So what are the main assumption, abstraction that we have in Zeno? Zeno is adopts as its core named data networking paradigm. So everything that deals with Zeno needs to have, the data needs to have a name, okay? And to a name, you associate a value. So the first main concept that you have in Zeno is a resource. So it's a named data, so that basically it's a key value. For example, it could be that you've got your temperature sensor, your kitchen, be home kitchen sensor temperature as a key, and the value will be, for example, 21.5 degrees Celsius. The second concept that we have in Zeno is a publisher. Let's take a water analogy. You can see that a publisher is a spring where data comes out from a publisher. And it's the spring that decides when to publish data. Okay, like a spring is decides how many data and many water is going to flow through the spring. And on the other side of the spring, we've got a subscriber that is a sink. So you've got data that come out from the publisher and they flow until the subscriber that is a sink, right? And then we've got a queryable. A queryable, as a water analogy, is a well. So you've got the water there, but it's you that decides when to pick it. It's not the publisher that pushes it to you. So let's try to see this with an example that will be clear. So this is an example of Zen infrastructure, where we've got multiple nodes. So this is our routed infrastructure, where we've got sensor, for example, with the thermometer there, and some handset, and some storages that are plugged into the network. So the example here is that let's imagine that we're at the Louvre Museum, and we have got different sensors in every room, in every floor. Okay. So what happens if we've got a sensor that publishes data? Okay. This sensor is publishing data to the key Louvre 142 sensor temperature. You can see that we have a set of subscribers, that in this case 2, that are subscribed to the same key here, and to a wildcard key here. So it means that this subscriber will match any type of room or floor that of the museum. So this is, you could see as a pattern matching, right? So it just expands to it and match everything that's in the middle. You can see with Zeno, as soon as it is published, the data is dispatched to the subscriber. And you can see I've got subscriber, but also a storage here that acts as a subscriber plus a queryable. So you could see a storage really as a combination of a queryable and subscriber. So it receives data as soon as it's published, but since it's a queryable, it's a well, you can get out data whenever you want. Open a little parenthesis here. In Zeno, a storage for us, we act as a front end for storage. So we don't implement any type of storage backend. So it means that here, behind the storage, you could use InfluxDB if you want to have time series. You could have in-memory storage or just do some caching. File system if you want to store your data on a file system, or any type of backend you might think of. Okay, we really act as a front end for geo-distribution of data. At the same time, we've got a second thermometer that publishes data, this time on the second floor. And you can see that we've got this data going to the other storage that stores the data from second floor. And we have got also a subscriber here in the bottom left that is sleeping. So in Zeno, we also support devices on duty cycle. So it doesn't mean that you need to be awake to receive data. The infrastructure can temporarily cache it for you. So when you're ready to get the data, you just wake up, you ask for the latest data, and you get it back, and you can go back to sleep. Now, assuming that we've got my operator, the museums, that wants to get the information about the temperature. So what it does, this answer that we call it querier, it means that issues a distributed query in the system to Louvre star 42 sensor temperature. This query is then dispatched to any matching storages in your infrastructure. So here and up there. And the reply are then sent back to the query in a consolidated manner, and you get all the response. So let's move quickly in a a glimpse about performance. So this is, as I said, Zeno is an open source project. You've got all the codes, you can test it and run it. And despite all the functionality that it provides for geodistribution, for pub, sub, etc., we really took care also about the performance that we can deliver with Zeno. So performance, what we mean? On the one hand, is about while performance. The other one is throughput and latency. So you see that in Zeno, every data has a name that could be arbitrarily long, but this is not quite efficient. So we've got an automatic mapping between long strings into smaller integer that are ID automatically done by the protocol itself. In such a way, on the wire, you can really reduce the overhead, the footprint of the protocol. This brings us down to the minimal wire overhead for all those functionality for 4, 6 bytes only by Zeno, depending on the configuration, but no more than 6. Okay. We've got high throughput, so here you can see on this graph that for different payload sizes, we've got a number of messages per second. For very small messages, like 8 byte messages, we can easily do 4 million messages per second in transmission. And these tests are done over a physical network, 100 gigabit per second Ethernet network. And as soon as you increase the payload size, you've got that you're basically saturating your machine and your network, and we are topping around 50 gigabit per second. Just a remark here, in iPerf on the same machine, so iPerf throughput, you are at 60 gigabit per second, so not that far. And same thing for latency. Here we've got for different arrival rate of your latency, and say that here we've got the ping half measurement that is about 6 microseconds. Here about all the processing, about publications and subscription, we're around about 35 microseconds, one hop. And the last thing is about some highlights on the Zeno protocol. So what we have here on the videos. So you were saying before that we can go on a constraints device. Okay, this is a Turtlebot running ROS2, and here what we have on the hand is an Arduino that is a battery powered. And basically, what we can get is that we've got Zeno running here, Zeno running here, and we can get commands and controls of the robot through microcontrollers down to the robot that through, in this case, a wireless network, and everything was battery powered. Here is part of the footage of the Indy Autonomous Challenge. So it's the first fully autonomous race car that race that happened 1 month ago in Indianapolis. So this is real Indianapolis. We got Indy cars, so fully compliant Indy cars with instead of having a pilot, just having a PC inside that fully autonomous driving. And all the communication were happening from the car to the pit lane was going through Zeno. Now, everything is so nice so far. I mean, but we haven't talked about AI yet in this part. So we just talk about how to move data. We've been seeing today a lot of presentation about how to build pipelines and how to really bring together. Here, just to, as I started with the first slides. So another comment from KCD. So check it out. I made a fully automated data pipeline that collects and processes all the information we need. It's a giant house of cards built from random scripts that will all completely collapse the moment an input does anything weird. It might not be. I guess that stuff, oops, just collapsing, you know, I can patch it. So we have seen a lot of work done on pipeline, but most of the technologies that have been used nowadays, also in some presentation, are pretty much cloud-centric. What happens when you want to distribute your AI down to the car? And some of the AI needs to interact with something at the edge, and the edge needs to interact with something in the cloud, or only the cloud with something on the vehicle, and any combination we might think of, right? So what happens? We end up with a very complex workflow. And how to deal with that? How can we have a system that doesn't require manual patching, building a giant house of cards that collapse the first time that you get a wrong input? So this is part of the work that we are doing with Zeno Flow. So what is Zeno Flow? Zeno Flow is still part of the Eclipse project, Zeno, right? So it just builds on top of Zeno to provide a data flow framework to easily develop and deploy decision-making application from the cloud to the device. Okay? Through Zeno, we have got the capability really to have data communication from the tiny sensors, Arduinos, up to the edge in the cloud. So we're just adding this on top as this framework in order to really provide this end-to-end data flow framework. Regardless, you're running on a vehicle. For example, in a vehicles, I've seen someone presenting that, okay, let's build everything in a Docker. If you go in a drone on a vehicle, you might not be able to deploy a Docker image. So how really you model it? For the ones that are not familiar with data flow programming, we can say that data flow programming represents computation as a graph of connected agents that can execute concurrently. You can see the next slide's representation for that. For the guys that are familiar with that, you just need to know that with Zeno Flow, we support CAN process networks as a model, and also universal data flow computing model that is NIALD, that was published by Microsoft a few years back. So data flow in a picture. So basically, you get your application and you model it like a graph, where you've got different stages of your computation that can be chained together. And you've got the data that is generated from a source, and it flows towards a sink. In the middle, you might have arbitrarily complex graph, where you can take arbitrarily complex decision. So it's just up to you when design your application, what kind of graph, what kind of decision path you wanna take. From a developer point of view, so what does this imply? That when you develop your application according to data flow programming, you basically focus on your node, so the computation that you need to do, and how to interconnect them. All the communication, so where data is, so location transparency I mentioned before, is provided by the framework itself. How to make the real data delivered from one node to another, this is inside the framework, and in this case, provided by Zeno. So what are the concepts in Zeno Flow for what concerns this graph? The first things that you see when operating with Zeno Flow, that we've got a Zeno Flow node. In literature, it could also be called operator, okay, in data flow programming. But for what your concerns, you've got your function, that is the computation that you need to perform. And you expect a set of inputs that needs to be computed. In Zeno Flow, you can decide if any input might trigger the computation. You need to wait for all three, or just a subset of any of them, right? So it's you that decides what is the input, what are the conditions that trigger the computation, okay? So there was an example from the Aura presentation and say, okay, we've got data coming to the cloud, and I need to know when to trigger, for example, the computation, or then to the action that an epileptic crisis happened. So this could be modeled, for example, with these input rules and the output rules. So it means you receive some inputs, you do some computation, and also you've got some output rules that decides which output to trigger, all of them, just one of them, or none of them, depending if some conditions were not satisfied. Now, Zeno Flow graph is, you take different multiple Zeno Flow nodes and you interconnect them together. What can we do in a Zeno Flow graph? So in Zeno Flow, we support loops for data flow. That means that you can get iterative processing and to keep a counter, for example, to do multi-passage object detection or whatever you might think of, right? Just for control, for feedback. We've got deadlines. So why deadlines are important? Specifically in the case of real-time or safety-critical system, it's important to have this notion of to be time aware. So it means that think about an autonomous vehicle that needs to plan whether to turn or not, or to take some action. It's useless for that system to make a decision based on 10 seconds old data. Okay, it means that the data is no longer fresh, it's stale, so the computation took so long. That means if you have, for example, a stage, there's some input of the camera, object detection, motion planning, you might decide that, okay, the object detection took too long, so I can go on with a fallback mechanism depending on how it's designed. So the deadline concept is pretty important for when you want to react also to errors that happen in the network. For example, also for tolerance, you might have that the node went down, the process crashed, or simply the network went down, but still you want to be able to keep going with all your overall system. And the last point is composability of the Zeno Flow graph. So you can compose your graph and represent a graph as a composition of multiple subgraphs. So you can get a really complex system because you can compose it as you like. So you can take, for example, this graph, and you say, okay, this graph now is one logical node, and this logical node could be, for example, this one. So let's see some example how we can use it specifically for AI. These specific slides are also part of the output that we are doing in the Demon projects. For we've got a mini AI expert working on network intelligence, especially for networks. So what if I've got multiple models that I want to test out in parallel, and I want to measure the time that I require for computation or the accuracy that of different models. So I can choose, or for example, also for quorum. I've got different models. I want to have a quorum-based decision. So if 3 out of 4, for example, in this case, are okay, well, it should be an odd number, but okay, let's assume that we've got 2 out of 3, the same decision, so that's my decision. So with Zeno Flow, you can compose the things in that way. Also adding, for example, a concept of deadline. So perhaps the most accurate decision takes too long, so it's no longer valid. So I don't need it anymore. It's better to have a suboptimal result than a late result sometimes. The same thing is, since we have got composability, you could see that whenever you have got your model, you can, as an output, you could have the result of your computation on one hand, but you can extract the features of your models, for example, specific computation on the other hand. You've got a separate subgraph to monitor how your model is behaving. Or in case of having some models in production, since again composability, you might have one model that is running, is taking a decision. So let's say on the data plane, really going on, and you might simply add a new subgraph that for training a new model, for example, for new parameters, and you just feed in it with the same data that is going through the running and the deployed model. So this is become pretty complex, okay, when you apply it, for example, to autonomous vehicles. So this is a picture from one of the recent project, was from Berkeley, the ERDOS project, and a pilot that models the autonomous vehicles pipeline, let's say, all this data flow with all the steps and type of interaction and dependency between different steps in terms of time link, data dependency, etc. For example, traffic light detection, traffic sign detection, object tracking, motion prediction, localization, mapping, trajectory planning, behavior planning, etc. And if you think back that this is only one part that can happen in the car that then needs to be, for example, integrated or enhanced by something at the edge, and probably also for data analytic purposes, for example, something in the cloud. So the type of graph that you end up to having with can become pretty complex. So, but through the capability of training, really, the composability of that, it becomes to be manageable across heterogeneous systems that really go from the car to the edge to the cloud. So this is a demonstration that we did. So this is not a live video. That means that it was a camera that registered the data, and we are feeding it into Zeno Flow pipeline for implementing object detection and then traffic planning. So this was generated with a 4 stages pipeline, and here you can see the real-time results of your pipeline with object detection and motion planning. So to arrive at the end of my presentation is for where are the fields where we, with Zeno, we really have the application domain? So just focus mainly on AI, on the autonomous vehicles in this presentation, but really we've got application in autonomous agriculture, we've got for smart city, and for example, and smart transportation as well. For example, another pilot that I didn't mention that was done the past month together with the guys from IMEC in the scope of a Demon project, that we've got the smart road tested on the ring road of Antwerp here in Belgium, where we were using Zeno really for data dispatching through the edge infrastructure on the cars and the centralized cloud. And as well as medical application, anyway, robotics, smart grid, and aerospace. So final thoughts on this. We can wrap up that Zeno is an innovative and performant protocol that solves some of the problems that are at the very core of IoT and edge computing, so data distribution, data centralization, and merging, really blending together different data patterns, including storages. And on top of that, we've got a Zeno Flow that is also a modern flexible data flow framework that solves some of the issues of performing distributed AI along really the cloud to device continuum. So not only in the cloud, but when we get out of the cloud, you need something more. And if you look, if you like Zeno, just go to our repo, GitHub, and the clips, and start hacking some code. And if you have some references, we are going to upload these slides on SlideShare. So we've got links to our webpage, to our GitHub, our Gitter community channel, and that's it. So thank you very much for. And if you have any question, please.
Question. I think that's really interesting to see the indie autonomous challenge, because it looks like Zeno is not the only project that was the only Eclipse project that was in the car.
No, it wasn't.
There is a Cyclone DDS.
So there was, for what concerns the communication, there were two main projects, right, in the autonomous challenge. So one was Cyclone DDS. Cyclone DDS is an implementation, open source implementation, again, under the umbrella of Eclipse, of a DDS protocol that, for the ones that are familiar with the ROS2, Robotic Operating System 2, is the default middleware for communication for ROS2. And Cyclone DDS were used inside a car and at the pit lane. Now, DDS suffers from some scalability and reliability issues when going over Wi-Fi and going out from a closed system. So what we were doing is we're using Zeno to bridge the communication from the car at high speed to the pit lane in such a way people were able to use all the ROS tools, for example, monitoring and debugging, etc., for really the robotics control part that was transparently bridged from over the Wi-Fi.
Over Wi-Fi?
Yes, it was a Wi-Fi implementation by Cisco.
Was working only when the car was close enough to the pit lane, or?
No, that's, I mean, they mounted in the whole Indianapolis on the truck, multiple antennas. Wi-Fi. It was from Cisco, a fluid mesh from Cisco. So we were providing Wi-Fi connectivity, low throughput Wi-Fi connectivity, because 300 kilometers per hour, you cannot afford to get more than a couple of megabits, no more than that. So being quite efficient and be able to really have location transparency without doing anything more than just accessing the data, because everything is managed really from the system itself, was extremely important.
Then we went to the motor, and I and my question is, would you see the motor as a way, not directeur, qui a réussi comme architecture compliance, and thinking of deadlines that could promote, describe my SLA, for example, and then find the corresponding deadline, and then to promote.
So just repeating the question for the sake of the guys connected online. So will they see Zeno Flow as a way, as a tool really for compliance, for example, towards SLAs and especially for deadlines? So what Zeno Flow provides is the capability to react when a deadline is missed, okay? Such a way that you build your software around that. What if your SLA, even if you try to do the best for your infrastructure, is not satisfied, okay? So Zeno Flow per se is a software application, right? That needs to be deployed then inside, for example, Kubernetes, and Docker, bare metal, or any other type of deployment, but per se doesn't guarantee the fact that you comply with the deadline. That is the network underneath, and it's the infrastructure underneath that needs to be sufficiently provisioned in such a way you comply with the deadline. But it provides you the means, all the hooks to say, what if the deadline is missed and I don't want to crash everything? I'm able to detect that something went wrong. So try to interface. I see that. Yeah.
I do understand some stuff. The way was define the mistake, but I think you are in a way to describe it as well.
Yeah. So basically, when you develop your application, and especially if you are developing application that do some kind of decision making or control action. So usually you've got a requirements in terms of what is my time window where my decision is acceptable. Okay, in that way you can express it through Zeno Flow, that you can define the deadline in such a way that next stages can see that everything is working as expected. Okay, so it really comes down to the model of your algorithms, model to the application, and Zeno Flow provides you a way to express that constraints and a way to make your next stages aware that something went wrong or everything is good. In such a way, you can take actions and to not stop everything that you are doing. There's time for another question?
Yeah, go ahead.
Okay. Sensor. So repeating the question, so can Zeno Flow can be used through deadline and deadline features to be used for reconfiguring my local architecture that doesn't need to be semi-distributed? The answer is yes. I mean, you can, Zeno doesn't impose the decision that you need to take, right? So for what concerns Zeno, it's you that defines this function that goes into a node. So you can receive an input that something went wrong, and then you decide how to interpret that information. And then if your output of your node is, let's reconfigure my local system, it could be done. So it's you that defines that what does it mean to get an output output 1 instead of output 2. So the answer is yes, you can do it.
Yeah, maybe one last comment. I think that Zeno was partly at least developed in the context of the research project. Is that statement or?
No.
Okay, so forget about my comment.
I mean, we have got involvement also in research projects. I mean, one is Demon that. Okay, just takes too long to go back. Demon is one of the research projects. We are involved in more research projects, so we continuously involved with the research institutes, other industrial partners, university to bring Zeno. And development comes from, it's not mainly done in research projects, but we've got collaboration research projects that allow us, for example, in this specific use case, and specific case of a daemon, to understand what is the impact of your infrastructure. So what is the impact of your data dispatching technology towards the AI and optimality of your AI model. So how can that impact and limit the optimality, the accuracy, for example, of your AI model?
Okay, good.